Hello guys, long time no see. First of all, I want to apologize because although this midterm review was supposed to schedule for today, but I was going to post it on like Friday or Saturday. However, this particular note took me so long to write, so that's why I have to postpone the posting today. So anyway, sorry for that. Let us start the review process. So as usual, there is three part of this review article. The first part is introduction about the core concepts and basically a formula sheet for what you guys will have to understand and memorize in the quiz, in exams. And second of all, which is the major component of this video, is examples. So this time, due to the fact that there's too many things I want to cover, I want to try to have you guys review on. So I will split this midterm review video into two parts. The first part will be concerning chapter 14, which in this case is on the optimization problem. And for the second part, we'll be covering different types of integrals and how we evaluate them. Okay. As usual, the studying method is quite direct. So you try to review the concept first, ask yourself what are the definitions, what are the terms, what are the algorithm that you can apply. And second of all, you work on the problems. First of all, you should be able to work on all problems in the suggested assignment. And maybe you can, if you have time, to do the problems in this particular article. I will obviously provide some answer key so you can see if you are correct or not. Lastly, yeah, oh yeah. So yeah, these are the two things I mentioned. To do the assignment first and then do the this extra exercise in this review sheet. So basically, if you're like really familiar with this problems, I would say you can get an A band range easily. So the difficulty will be similar to the midterm one, and it will remain the same in midterm two, in midterm three, and the final exam. Okay, so yeah, that's the chapter 14 for this video first. So basically, chapter 14, the remaining two topics are optimization problems. One is without constraint and one is with constraint. So let us first review the formulas and actually the algorithms. So to find maximum and minimum values, there are two types of extremals. One is the local extremal and one is the global or absolute extremal. So for local extreme value, it's basically some point where the function achieves a value that is locally larger than any value near the point or locally smaller than any value near the point. So basically, this will be a local maximum and this will be a local minimum. They might not be absolute maximum or minimum, for example. In this case, this guy is still a local maximum, but it is no longer absolute maximum because somewhere here is larger than this function value. Okay, so how do we determine and how do we find local extremas? So there is this algorithm. First of all, local extreme value must satisfy this equation, which is that the point must be a critical point. So a critical point may not be a local maximum or minimum, which we will cover soon enough, but a local maximum or local minimum must be a critical point. So critical point, by definition, is a point so that the gradient is zero. This also works in three-dimensional space, and that it might be not exist. So, for example, an absolute value function admits a point which is not differentiable, right? And obviously, this point serves as a local minimum, actually an absolute minimum of this function. So there is a possibility that the absolute maxima or minima achieves at the point where the differential does not exist. However, in most cases in our problems, the function will be differentiable everywhere. So you don't really have to care about that. The only thing to memorize is that critical points are the points where when f is differentiable, the gradient has to be zero. Okay, so now we have a bunch of points, right? After solving this equation. So this typically will be a two variable two equation. You can solve for x and y. There might be multiple solutions, depends on the degree of the equation. And then how do we distinguish between this grid of points? There will be three different natures. One is local maximum, one is local minimum, and one is neither. So how do we do that? We apply the so-called second derivative test. It is quite simple in the one variable case, and in the two variable case, it is a little bit more complicated. So we define a thing that is called the hash determinant, which is given by, in this case, triangle F. I think in the textbook it is DF. I don't want to be confused about D in terms of the hash determinant and also the differential. So I use triangle F. So triangle f x y is a function defined by f x x x y, which is the second differential of xy of f in terms of x and x, and f y y minus f x y squared. Right. So how does this quantity help us? So you can do this particular algorithm. If the Hessian determinant is positive, then this point must be a local maximum or minimum. And to distinguish those two cases, you can see whether fxx is positive or not. So if fxx is positive, then it must mean that you have a local minimum. If xxx is negative, then it must mean that you have a local maximum. So you might want to ask, what if fxx is zero? It's actually not possible because you see that this guy is defined by this formula, right? If fxx is zero, then hash determinant must be negative or zero. So this case would not happen. So if the hash determinant is positive, then you must have these two cases. So it's not possible for fxx to be zero. And if the hash determinant is zero, is negative, then the point x dot y naught is a saddle point. That is a point which is neither a local maximum nor a local minimum. And if the hash determinant is zero, then your problem is inconclusive, meaning that it might be local minimum, maximum, or saddle point, and it must be one of them, but you don't know. You cannot derive that from the second derivative test. And obviously, there is some method to deal with that. You can apply the so-called like third, fourth, and multiple differentiation tests, depends on the regularity of function, but we won't cover that. In almost every cases, you can do these two guys. You can determine these two guys. You can determine the critical point is a local maximum, minimum, or a saddle point via this algorithm. Okay, so let us do this really fast. First, you evaluate the Hessian determinant at the point, at the critical point, and then if it is positive and that fxx is positive, then you must have a local minimum. On the contrary, you will have a local maximum. And if the Hessian determinant is negative, then you have a saddle point. Okay. And we usually like to list this out by a table, which we will see later on, and it can fully show that at which critical point do you have which behavior. Okay. The second type of problem is to find the extreme value, the absolute extreme value on a particular domain. This domain is usually closely involved, and mostly it will be like a regular domain in a sense like a rectangular, a triangular, or a circular. Okay. Okay. So again, the first thing will be to investigate points inside the domain. So we find every critical point inside the region omega. So if you're dealing with a rectangle, then everything will be considered expect anything outside the boundary and on the boundary. We only care about something inside the boundary. Okay, next we parameterize. So we will talk about parameterization in just a few days, maybe in chapter 16.1 or 16.2. So parameterization in some senses to reduce a similarly two-dimensional object into a one-dimensional object. For example, and the boundary of omega, say omega is a rectangle, then actually the boundary is just lines, right? So we want to understand them as lines instead of a object in the 2D space. So that is called parameterization. Recall that in chapter, I think, 12, we investigate a lot of lines and curves in the space, right? And we can do some parameterization on them to make it into a one parameter thingy, right? In terms of like T or S. So that's what I want to try to mention. We want to represent this curve, this boundary curve, by a variable. For example, if it is a rectangle, you can use T to solve for the line. For example, if it is a circle, you can use cosine, and sine data to represent the circular object. So anyway, you try to write down the equation of that particular line, the boundary of omega, in terms of a one variable, like T or S or data, and then you restrict your function f onto that space. For example, some line or some circle. Okay. And then it becomes a one variable extreme value situation, right? So as usual, you want to test the critical point within the boundary and also test the endpoints A and B, right? After you find all this interior point in omega and also interior point on the boundary and also endpoint on the boundary, then we compute the function value for all these guys. Now we determine which one is the largest one, which one is the smallest one, and we can deduce the absolute maximum minimum. Okay. So the only difference between this absolute extrema algorithm and the local extrema algorithm is that we have to care about boundary. Boundary is very delicate, and there might be extreme value achieving on the boundary. Okay. The second topic in this chapter 14 is Lagrange multiplier. So this is a very special type of maximize optimization problem, which is we want to maximize or minimize some function subject to a constraint g of x, y. So the idea is quite simple. Actually, it only begs the idea that these two guys, this guy will achieve its optimum value on this curve whenever they are tangent to each other. Under that idea, this is the algorithm that we have provided, the so-called Lagrange multiplier method. We consider the so-called Lagrangian defined by L xy with an extra argument. This is called the Lagrange multiplier, defined by f minus lambda g. Actually, plus g will do. The value of lambda have some meaning, but we won't discuss it here. So, but yeah, let's do the convention Lagrangian, which is L equals f minus lambda g. And then we solve for the gradient. So we set the critical point for L, which means that you want to take gradient on both sides. Don't forget this gradient is in terms of x, y, and lambda. In x and y, we get gradient of f equals gradient of g times lambda. They're parallel, basically. And that g must be 0. So this is basically the idea that we want. Those two curves, f and g, are tangent to each other. They share the same direction of gradient. And also g must be 0 because we're only investigating points on that curve. And be careful, we obviously have to verify that the gradient of g is not 0. So that is sort of a pre-requirement for the Lagrange multiplier to work. So in the midterms, I might ask you in a subproblem to verify this. So I will ask you, okay, apply Lagrange multiplier to solve this. The first step is to check that it's applicable. If the Lagrange multiplier is not applicable, then there is nothing to discuss. So that first thing to check is very important. And there's that. After solving the critical points, usually there's one more step, which is to check whether the problem is well defined in the sense that there is actually a maximum or minimum. But this step is a little bit difficult in general, and it's not what we focus in this particular course. It might be important afterwards. So for any problem in this particular Lagrange multiplier section, I will emphasize that there is a maximum or a minimum value. So you don't have to verify whether it is or not. That is saying, after you find all the critical points, the remaining task is simply plugging all those guys into the function f and to see which one is the largest and which one is the smallest. Okay. So this is what I mentioned here. Compare the function values, which you get in the second step. Okay. So this is another type of problem. It is actually quite similar. So now we're not only subject to one constraint, we're subject to two constraints. And in general, this will only happen in 3D space because subject to two constraints in a 2D space is usually just points. That'll be a kind of a tedious problem. So we want to make things more interesting. A intersection between two level set of two functions usually is a curve. And we want to evaluate the maximization or minimization of this function f on that particular curve. So we do the same thing. We consider Lagrangian L. Now we have two Lagrange multipliers, lambda and mu. And the Lagrangian L is given by f minus lambda g minus mu h. And obviously, we have to verify the condition, which is that the gradient of g and gradient of h is never 0. Never 0 on that constraint, okay, in this curve. And that those two gradients are not parallel forever on the level set. If those if those requirements are met, then we can apply this Lagrange multiplier method. And it's basically saying that this both have to work and that the gradient of f is we usually call this a linear span or a linear combination of the gradient of g and gradient of h. And so this actually have a z here. I will fix that later. So nabla of f x y z equals to lambda nabla g plus mu lambda h tells you three equations. And g and h being 0 gives you two equations. You have a natural 5 equation and 5 variable, so you should be able to solve that. And obviously, the last step is to evaluate this critical point on f of x, y, z, and to see which one is the largest one and which one is the smallest one. So, yeah, basically, three type problem. One is the local maximum, local minimum, and one is the absolute maximum, absolute minimum, and the last is the same thing, but on a constraint. Right. So we will discuss chapter 15 afterwards. Let's do the exercise from chapter 14 first, and to see what we can cover. So those are classical problems. You're asked to find the critical points of f of x, y, and determine its nature. So by determine its nature, I mean to verify whether it is a local maximum, local minimum, or a saddle point. So basically, we just follow the algorithm and be careful with the solving of equation. If you are wrong at that critical point solving, then everything just goes wrong afterwards. So really be careful with that. Okay, let's dig down the solution. So for this two-variable situation, let us see whether the gradient is 0 or not. Taking differential with respect to x, you get 3x cubed, 3x squared, plus 6x minus 9. And we set it to be 0. And then by differentiating with respect to y, you get minus 3y squared plus 6y to be 0. And then it's a two-variable two equation, which are both quadratic. So you can do some simple thing like factorization, which you get x must be either 1 or minus 3, where y can be either 0 or 2. So be careful. This two has to be simultaneously held, right? So this two has to be simultaneously held. So there's 4 pairings, 1, 0, 1, 2, minus 3, 0, or minus 3, 2. So there are 4 critical points to be considered. And as we mentioned, the next step is to apply the second derivative test to see whether you have a local maximum, minimum, or saddle point. So by definition, the Hessian is defined by fxx, fyy minus fxy squared. And yeah, basically plugging in the corresponding differential. Say we differentiate this by x again, you'll get 6x plus 6. Differentiate this by y again, you get minus 6y plus 6. And obviously, if you differentiate this by y or differentiate this by x, you'll get 0. So there's no cross terms. So this is a particular nice case. Having this, you plug in the 4 points, and you get this particular table. At 1, 0, 0, you have a positive Hessian and a positive fxx, and so on and so forth. So I really encourage you to try to write down this table because it will make things easier, both for both of you and me. For you, it'll be easier to see whether you have written down the correct implication or not. For me, it'll be easier to grade, basically. But this is not required. If you can write down the Hessian for this guy is 7.2 and that fx is positive, so blah, 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 then I'll be appreciated enough. So under this table, you can see that these two guys are saddle points. This is not really important if they're saddle points. And this two guy gives us absolute minimum and absolute maximum. So local minimum and local maximum. So basically the function achieves a local minimum at the point 1, 0 and local maximum at the point minus 3, 2. And also the 1, 2, and minus 3, 0 are saddle points. Right. So let's do our second problem. So these are all similar. I just want to involve as many as I can and want to try out different functions. For example, the first one is a polynomial, second one is exponential, and the third one is a trig function. So for the second case, you have e to the minus y times x squared plus y squared. Taking differentiation, maybe I should copy this here so you guys can have a look. There's our function in consideration is e to the minus y x squared plus y squared. So if we differentiate respect to x, you can get simply 2x times e to the minus 1, which is here. And if we differentiate with respect to y, be careful, you have to do a product rule because there's two things in terms of y. Differentiate this guy, you get minus e to the minus y. Differentiate this guy, you get 2y. So that's all. And since e to the minus y is never 0, you can just divide that from both sides of the equation, which you get x to be 0, and x squared plus y squared minus 2y must be 0. Plugging this guy back to the second equation, you can get y is either 0 or 2. So there's exactly two critical points. One is 0, 0, and one is 0, 2. And again, it's a simple evaluation. You brute force compute the Hessian determinant, which in this case is quite simple. It is something always positive, and you have a polynomial here. By plugging in the critical points to the Hessian and also the fxx. So I want to mention, obviously, if you get a settle point, you don't have to evaluate fxx. This is just for completion. So in this case, we get this guy to be a local minimum. Both of them are positive, and this guy is a settle point. Okay, now for a third case, when we're dealing with this trigonometric function, so I believe I have already done this back in the video after Lagrange multiplier. So when I introduce more different optimization problems, I include this here just for the reason that I want to consider the case of periodic function. In that previous video, we considered the maximum and minimum of this guy respect to, I think, this domain, on this domain. But for now, I didn't restrict any x and y, so we can solve for general arbitrary critical points and critical values. So differentiate the function, taking gradient, you get this equality. And then this solving is the same thing as in the previous video. So we have y or sine, y to be cosine x. And by plugging that back in the first equation, you get cosine x, sine x to be 0. And this is basically telling you that x has to be a multiple of pi to the half integer, meaning that x has to be n pi divided by 2 for every n belongs to integer. Okay. Previously, we have distinguished this case by taking different n and see whether it is above 0 or not, or below 7 or not. But in this case, I didn't give you a particular region, so you have to consider all solutions. n pi divided by 2, where y is given by cosine x, and that is cosine n pi over 2. So there are actually infinitely many critical points, depending on n. Okay, and to evaluate the Hessian, it is quite simple. Differentiate this guy by x, you get 2y cosine x. Differentiate this guy by y, you get 2. Differentiate this guy by y, you get 2 sine x. And so the Hessian determinant is simply 4 times y cosine x minus sine squared x. Right. Now, the value of this cosine actually only depends on, okay, this is not a good language. Basically, this guy is periodic in the sense that when n is 0, 1, 2, 3, those 4 are the only value that you have. Because when n goes to 5, then 5 pi over 2 is pi over 2 plus 2 pi, right? So everything goes back by one round. So we only care about whether this n is divisible by 4 or having remainder 1, 2, and 3. So 4k, 4k plus 1, 4k plus 2, and 4k plus 3. At those cases, cosine will be 1, 0, minus 1, and 0, which correspond to the 1, 0, 0, 1, minus 1, 0, and also 0, minus 1. Those three particular coordinate points. Okay, and under that point, you actually have the same Hessian, again, because of the periodicity of cosine and sine, and you have 4, minus 4, 4, and minus 4. So this the particular point gives you set of points. And this the point actually both give you local minimum. And this particular curve has no local maximum. Okay? Right. So that'll be all for the finding of local maximum and minimum. I hope that will be sufficient. It is actually not really difficult. I would say the most complicated part is solving the equation. And just be careful when you're doing any factorization. I will set up the number to be simple enough so you won't get like very complicated solution. So when you have some complicated solution, be careful. You are messing something up. So go back to the algebra and to see if that level have any incorrect algebraic mistake. Okay. Right. Now we're dealing with the absolute maxima and minima. So in this case, I have two problems. One is some periodic function on a rectangle, 1, 3 times minus pi over pi, pi over 4. So this is where y belongs, and this is where x belongs. Secondly, we're dealing with a circular region. So we're dealing with a disk with center at the origin and radius 1. Okay, so pardon me. The first step, I label these steps based on our previous core concepts. So the first step is solve for the interior critical points. So that is first take the gradient of f. In this case, f is given by this guy. So actually it is quite separate in the sense that you can just differentiate this guy with respect to x. And you get 4 minus 2x to be cosine y to be 0. And later on, 4x minus x squared times sine y to be 0. So this tells you that either x is 2 or cosine y is 0, which means that y is always a half multiple. Okay. Actually, I'm sorry, this is not correct. Let me make this better. It does not affect the answer, but I have to make this better. So this tells you this is not correct. Cosine y being 0 actually tells you that y is half multiple. It must be half multiple in the sense that it cannot be y equals to 0 or pi because those give you either 1 or minus 1, right? So this will be better notation. 2 and let me write n plus half pi. That'll be better. N belongs to 0. Okay, it must be a half integer. And secondly, we have this guy to be 0. And that means that x is equal to 0 or 4, or y has to be n pi. Okay, so if sine y is 0, then y has to be n pi. That is true. So let us see the combination. This and this has to be held at the same time, right? So let us check. When x is 0, then obviously x cannot be this two guy, so only y can be n pi, right? So those are one of the solutions. 2 n pi. And now we are restricted inside a region, right? The region is given by this omega. So if it's 2 inside this region, yes. Is n pi inside this region? Only when n is 0, right? So for that particular pairing, we only have 2, 0 as a solution. Now, suppose y is given by n pi average, half integer of pi, then we want x to be 0, 4, right? So those are also critical points. 0 together with this guy, and also 4 together with this guy. However, 0 and 4 are outside this region, right? 0 is less than 1, and 4 is larger than 2. So those are not of consideration. The only critical point that lies in the region that we are interested in is T0. So there's that. Now we deal with the boundary. So on the boundary, there is actually 4 of them. This is a rectangular set, right? So actually, I have a figure drawn here. This is the set that we're considering. You have minus pi over 4 and pi over 4. Oh, sorry, 1 and 3, my bad. And this is minus pi over 4 and pi over 4. So we have a particular critical point in the interior that is to 0. And for the boundary, we have to be careful with these 4 different lines. For the first line, let me do y equals to minus pi over 4. So that's a horizontal line, this red line. And you can basically parameterize the line by x minus pi over 4, right? Because y is fixed to be minus pi over 4. So we fix the so-called f1x to be the two-variable function on this line, and that gives us a one-variable function. So you can find the optimal value of this function by a million times. In this case, I just do the standard way, that is differentiate it. And we see that the x has to be 2 to achieve, in this case, a global minimum. But if we do this blindly, we don't care about whether it is a quadratic function or not. Let us try just any point that is possible to be absolute minimum or absolute maximum. So in this case, it is the critical point, which is 2 minus pi over 4, and also the boundary point, which is 1 minus pi over 4, and 3 minus pi over 4. Okay? So actually, without doing this calculus algebra, we actually know that this is a quadratic function. So, and the coefficient for x squared is negative. So it actually achieves a global maximum at this point. And these two actually should share the same value because they go the same length from the central axis, x equals to 2. But for now, we don't care about like particular feature about particular function. It might be helpful, but I want to do this systematically. So we simply apply the same algorithm on each function, whether or not it is quadratic, linear, or some particular strain function. And actually, for the upper line, y equals to the power of 4, this blue line here, we have the exact same function due to symmetry, basically. And so again, you have three critical points. One is the interior one here, and the two are the boundary points. Now, for the left and right, where x is fixed, we have x equals to 1 or x equals to 3, which we get the same function, we get some function at 3y equals to 3 cosine y. And that again, you have the critical points being m pi, which is whenever sine is 0. And the only possible coordinate inside the region is when n is 0, so 1, 0. And these two are the boundary points. The same thing then happens for f4, which is the function evaluated on the right boundary, x equals to 3. Okay, so now what do we have? We have this point as a candidate, this point as a candidate, this point as a candidate, and this point as a candidate. I think that's all. Oh, that's here. And actually, there's not that many points because some of them share the same critical point, boundary point, right? So we see that these are the all boundary points, all critical points, sorry. This 8 point and this 1 point. So there's 9 values. And evaluation is quite simple. The function is actually itself quite simple. It is given by some function depends on x and some function depends on y. And that multiplication is quite simple. It gives us some periodic kind of flavor. So you see that some value are actually the same. And then we compare these values. Largest one is obviously this, and this, and this, which is the boundary. Okay, oh, sorry, the minimal one, not the maximal one. So actually, it achieves an absolute minima at this 4 points, the edges of this particular rectangle. And for the maximum, it is obviously 4, which is actually this point inside the omega. So it achieves the absolute maximum at the interior of omega, and also the absolute minimum at the edge of this boundary. So it looks like a ball upside down, like this. The maximum is at the midpoint, and you have minimum at the 4 edges here. Okay, now for the circular domain, we're interested in this function, 2x cubed plus y4. So the algebra is again the same, the algorithm is again the same. We deal with the gradient, which in this case is quite simple. The only possible critical point is 0, 0, and this happens to be in our domain. So the origin is one of the critical points. Now, for the boundary of omega, we will discuss this soon enough. So actually, you can do this by something like Lagrange multiplier or some more advanced technique. But in this case, let us do the most systematic one, which is by parameterizing the boundary omega. So there's different parameterization, and each have its benefit, have its virtue. For example, the easiest benefit, the easiest parameterization of this function will be something like this: the upper circle and the lower subcircle, right? Also, plus x and plus minus square root of 1 minus x squared. This reduces the boundary into a one variable function, right? However, in this case, I choose cosine psi to avoid the square root because I don't like square root. So let me do cosine theta and sine theta, where theta goes from 0 and 0 to pi. So we want to consider the function evaluated at cosine psi. I don't know why I write g here. What I want to write is actually g theta. Sorry for the typo. Is equal to f of cosine theta sine theta. And you get 2x squared plus y to the power of 4, right? So we now have a one variable function evaluated on this closed bounded domain, 0 to 2 pi. The method is the same. You find the interior critical points and also the boundary points. So let us take a differential, which you get 6 cosine squared minus sine theta, and 4 times sine cubed cosine theta. And factoring out the common term, you have 2 cosine sine and minus 3 cosine plus 2 sine squared theta inside. So either this guy is 0, or this guy is 0, or this guy is 0, right? This is a standard trig equation. To solve this to be 0, we might want to replace this sine by cosine because sine itself is given by Pythagorean theorem, 1 minus cosine squared. Sorry, right? And so by rearranging the equation, you can get 2 cosine squared plus 3 cosine minus 2. And that is a simple quadratic equation which you can factorize. 2 cosine minus 1, cosine plus 2. This is not possible because cosine is never minus 2. It's never smaller than minus 1, right? The only possibility is when theta is half. Sorry, when cosine theta is half. So that is theta either in the 60 degree or minus 60 degree. So this two equation gives you either 0, pi over 2, pi, 3 pi over 2, and 2 pi. And cosine theta being half gives you 60 degree, pi over 3, and also minus 60 degree, 5 pi over 3. Okay, so this will be our critical point of consideration. And you want to look at the graph, it looks like this. You have this 4 points due to the fact that cosine and sine must, can be 0. And these are the points where that quadratic equation is 0. And this is the interior coordinate that we want, interior critical point that we want. So now we evaluate those boundary critical point and also interior critical point, and you get that the absolute maximum will be, in this case, 2, evaluated by 1, 0 on the right hand side, this guy. And the minimum is, in this case, minus 2, evaluated on the left hand side, minus 1, 0. Minus 1, 0, this guy. Okay. So again, I would say in this case, the complicated part will be the solving of the equation and also the parameterization of the curve. We will be doing a lot of parameterization for curves and surfaces in chapter 16, so make sure you're prepared for that. For now, it is mostly squares, triangle, and circle, and I believe I have covered all of those cases in this note and also the note in the introduction for absolute maximum minimum and the note after Lagrange multiplier, which is more general optimization problem. So make sure you cover those and to see like how do you do the algebra in those cases. Okay, the next type of problem in this video is Lagrange multiplier. So we have done with the local and global extrema. Now let's do the constrained optimization problem. So constrained problem usually have a lot of methods to do, and I will try to cover those. Basically, the central idea is to apply Lagrange multiplier, and all the tricky kind of solution is applicable, and you can do that, but you must be careful with the condition that when you can apply that, okay? Whenever you're solving this type of problem, you have to clarify what have you used and why is your solution applicable? Because there is some problem where Lagrange multiplier is not applicable, and that does not give you a maximum and minimum. So you have to check the pre-requirement. Okay. In this first case, we're interested in the maximum and minimum value of x squared plus y squared subject to constraint, this particular quadratic polynomial. So the straightforward method is Lagrange. Oh, sorry. By the way, I have mentioned before that I will assume basically tells you that the actually extreme value exists. So you don't have to verify whether it exists or not. You can simply solve the algebra and find out the critical point. Largest one will simply be the maximum, and the minimum will simply be the minimum. Okay, so yeah, the first method here is Lagrange multiplier. So this is the target function. We put it here. This is the constraint function. We put it here together with the multiplier. So to check whether the Lagrange multiplier actually works, we take the gradient of this guy and to see that it is non-zero. So the gradient of the constraint is given by 2x minus 2 and 2y minus 4. The only possibility that this is 0 is when x is 1 and y is 2. However, this point does not lie on this curve, right? You can check that by directly evaluating it at 1, 2. So the curve G does not have 0 gradient at any point on G. So it'll be nice that we can actually apply Lagrange multiplier. So by solving the gradient of L to be 0, you have lambda 1 times x be lambda. So that is the simplification of this. I omit some steps. If we take differentiation with respect to x, you get 2x minus lambda 2x minus 2, right? Equal to 0. And that will give you lambda 1 x equals to lambda. Okay? I didn't include that because there's no space actually. So you can get the same thing for y. The only difference is that this is 4 here, so you'll get a 2 lambda. And lastly is g to be 0. So this guy has to be 0. So let us solve the equation. We have 3 variables and 3 equations. And don't forget that we're not in particular interested in lambda now, so you don't really have to solve that. If you can solve x and y, that'll be sufficient. So in this case, let us see, I want to divide this lambda minus 1 to here, and let us observe that lambda must not be 1, because when this is 1, then this left-hand side is 0, and this is 1, and y is obviously not 0, right? So this guy is never 1, never 0. We can obviously take a division where we solve x to be lambda divided by lambda minus 1, and y is a double of that. Now, by plugging this guy and this guy back into number 4, you can get a quadratic equation, which is 5 lambda times lambda minus 2 to be 0. And we can solve the lambda will be either 0 and 2, and plugging it back to x and y, you get 0, 0, 0, or 2, 4, 0. And now it's just testing. It tests 2 and 4 and 0 and 0, where you find out that x squared plus y squared is minimized at this point with value 0 and maximized at this point with value 20. So that is the standard way of Lagrange multiplier. You simply write down the Lagrangian, solve the critical points, and evaluate those critical points to see which one is maximum and which one is minimum. Now, the second method is in somehow more direct. We simply parameterize the curve and restrict our function on that curve. So this is actually the method that we have dealt before in the solving of absolute maximum. So we parameterize this particular curve in a one variable parameter equation, and we plug that equation into the function to make things into a one variable case. And then you are dealing with a one variable calculus problem, which is simple enough. So observe that this equation actually is a circle. You can do that by a simple complete of square. It is a circle with center 1, 2, and radius with 5. So you can simply parameterize that by, again, using cosine sine. You have 1 plus root 5 cosine theta. Y is 2 plus root 5 sine theta, where theta goes from 0 to 2 pi. So our consideration on on x squared plus y squared is given by f of theta, which is x squared plus y squared, And you can do the algebra to see that it is 10 plus 2 root 5 times cosine plus 2 sine. And to find out the optimized part, you can simply do the differentiation and see that the critical point only occurs when theta has tangent value to be 2. Since we only consider the range from 0 to pi, right? So there's only 2 points where tangent has 2 as a where theta has 2 as a tangent value. It is either inverse tangent of 2, which is somewhere in the first quadrant, or inverse tangent at 2 plus pi. So those are the 2 points. So evaluating these 2 points and also the boundary, 0 and 2 pi, which actually is the same point, you get these 4 values, which you see it achieves a absolute maximum at this point and absolute minimum at this point, which is the same result as this first method. So this second method is actually reducing things to a one variable case, and then we apply the one variable calculus kind of algorithm. Okay, the third method is pure geometry. So this is actually a sort of a high school solving, and it's just based on your observation on a circle. So since we're optimizing this function x squared plus y squared over this circle, we're actually just finding the furthest and the smallest distance within the origin together with points on this circle, right? So this is what I've written down here. We're essentially finding maximum and minimum distance from origin to the point on the circle. Okay. So actually, if you want to find a particular point which has some sort of critical points or say maximum and minimum distance within the point on the curve and some point, then if you connect that point towards the curve, you must have, it's a good example, you must have that the point and the origin, and a point connected to be orthogonal to the tangent line. Okay, this is not a good drawing. Like that. The reason is actually quite simple. If you are not orthogonal, so for instance, let us do this one here. So you have a tangent line like this that is not orthogonal to the red line. That means that you can always shift a little bit towards here or towards here to make to maximize to tune up or tune down your function value, right? So in that case, that point will not be either a local maximum or local minimum. That is why the intuition must be true, which is that if you want to attain a maximum or minimum, or in particular just a critical point, a critical distance within some point, together with another point on the curve, then connecting between the point and that extremal point must be orthogonal to tangent line. Or in a more straightforward way, the circle spanned by this radius with the point in consideration must be tangent to the curve. This is actually the idea behind Lagrange multiplier. So if, as I mentioned, if you want to evaluate some function on a curve, then the level set of this function must be tangent to that curve if you want to have a local critical point. So that is basically the idea. And since we're dealing with circle is a very good object. Anything passing through the origin must, any line passing through the origin must be orthogonal to tangent line on the circle. So what I'm saying is that anything that looks like this is orthogonal to the tangent line, right? So we're simply finding anything that is orthogonal to this particular circle. This is a circle in consideration, this guy. And also orthogonal to the circle spanned by x squared plus y squared. The level set, basically. X squared plus y squared equals to 2, 3, 1,000, something like that. And since we're dealing with circles that are the line that passes through the center for the circle here, and also a circle of this x squared plus y squared level set, which is concentric with center 0, the origin. In conclusion, we're simply drawing out a line that connects the origin together with the center of the circle 1, 2. So that is what I mentioned here. Basically, the level sets of x squared plus y squared are concentric circles centered on the origin. So we simply have to connect the origin together with the circle in consideration. And the corresponding 2 points will be the largest and the minimum. The largest and the small distance achieved by points on that curve, on that circle. So what is the curve? The curve is given by connecting 0, 0 and 1, 2, right? You can solve that easily. That is y equals to 2x, and it has to be lying on the circle. So we're finding the intersection, this guy and this guy. And it's very simple. You simply plug your 2x inside the equation, and you get 2 points, 0, 0 and 2, 4, which is kind of familiar, right? It happened somewhere here, 0, 0 and 2, 4. So we get the same thing. You achieve a minimum value at 0. The distance between the origin and the origin is simply 0. The distance between origin and somewhere that is farther away from the origin is 2, 4, giving 20. So this is a geometrical way. And these three are all acceptable answers, but if you want to apply method 2 or method 3, be careful on the condition. So for example, you have to state very clearly that you're reducing everything on a curve in this second parameterization solution, and we're considering everything defined on 0 to 2 pi. So everything reduced to a one variable calculus, which you can test the interior critical point together with the boundary point. For third method on this geometry method, this kind of explanation is crucial. You have to know why. That gives you the answer. So I would say that intuitively, this is obviously true. If you want to find the absolute maximum, the longest distance from the circle and the origin, obviously you have to connect this guy. But why is that? Is it just because what I mentioned? You have to have a tangent between the curve of this red circle and also the curve of the level set of this x squared plus y squared. Okay. Right. So for the second example, we want to find the maximum value of this x squared plus yz plus xz, subject to the x plus y plus z equal to 6. So as I mentioned, this actually has an extreme value, meaning you obviously have a maximum value. This is not really, I mean, it is somewhat intuitive, somewhat not. So you can see that x plus y plus z actually can provide you a very flexible choice of x and y and z. And this guy actually has no minimum. And to verify that it has a maximum, we can see that afterwards. So let us first start with the easiest method, which is Lagrangian method. Easiest in the sense that you don't have to consider any extra condition. You can simply apply the algorithm I mentioned to you guys. So let us consider the Lagrangian Lxy lambda given by xy plus yz plus xz minus lambda times the constraint. So first of all, again, let us verify that this is applicable. The gradient of this guy is always 1, 1, 1, which is never 0. So the multiplier method is working. Taking gradient, we see that x, y plus z is equal to lambda. And the same thing happens for 7 and 8. And also you have to satisfy the constraint. So x plus y plus z is 6. So by 6, 7, 8 here, say we're dealing with this two equation, y plus z will be equal to x plus z, right? So that is x equals to y. And the same thing occurs for 7 and 8. So you can simply get, at the critical point, you must have x and y and z to be the same. Plugging in back to this guy, we can get those values are just 2. So the absolute maximum, which as I mentioned, you don't have to prove it is a maximum. You simply plug your 2 inside. You get 2 times 2 times 3, and that is 12. So the maximum of this guy, subject to this constraint, is 12. And I have mentioned here that you don't actually have a minimum. Because, for example, by this very naive setting, z to be 0, x to be t, and y to be 6 minus t, then your function xy plus yz plus xz is simply t times 6 minus t, which goes to minus infinity whenever t goes to infinity, right? Actually, plus minus infinity. If t goes to minus infinity, then this guy goes to minus infinity, and this guy goes to plus infinity. So either way, you can get a minus infinity value, meaning that this guy has no absolute minimum, okay? It goes towards negative value when it goes along both sides on this plane. Okay? Right. Now, a second method, we do parameterization. So since we have x plus y plus z equal to 6, right? So you can simply solve z. Z must always be 6 minus x minus y. So we simply want to solve xy plus yz plus xz, which is xy plus x plus yz, where z is given by this guy. So for now, this is actually a constraintless maximization problem, right? We don't have any constraint on this x and y. So you can just do anything we have done before. We find the critical points, which you get, there's only one, there's 2, and plugging it back, you can get the value to be 12. So if you want to do that, that is also okay. That is the exact thing that we solved. We parameterize z using x and y in this case. Okay, the third is by the so-called Cauchy-Schwarz inequality. I forgot to include here. I will include a link here. Forgot to do that. Okay, I'll include the link here and here. So I have introduced this in, I think, lecture on the Lagrange multiplier or after that. And basically it tells you that the dot product between two vectors, sorry, let me just write it down. The dot product between two vectors, taking absolute value, is always less than the length of u times the length of v. This is basically equivalent to saying cosine theta is less than 1 somehow. So after that, you can do the algebraic version of the inner product of the dot product and you have this type of equation. Let me write it down. A1 B1 plus A2 B2 plus A3 B3 squared. This is the dot product. Is less or equal to A1 squared plus A2 squared plus A3 squared. This is the squared of the length. B1 squared plus B2 squared plus B3 squared. Okay. And why is this useful? Because we see that this kind of cross term is actually given by this guy squared minus this guy. Because this thing expanding simply gives you x squared plus y squared plus z squared plus double of this guy. And we have already known that this guy is fixed by 6. So 6 squared is 36. 36 divided by 2 is 18. So this is actually given by this. To maximize this, we simply have to minimize this. So by Cauchy-Schwarz inequality, you see that x plus y plus z is less or equal to this guy, where this is given by 3. This is given by 3. And this is given by 6. So x squared plus y squared plus z squared is larger or equal to 6 squared divided by 3, which is 12. And let me mention here, this actually is achieved when, as I mentioned in the lecture video, you have a parallel between these two vectors. So x divided by 1 has to be equal to y divided by 1 equal to z divided by 1, which means that x and y and z are all equal. So we see that the maximization of this guy is 18 minus half of the minimization of this guy, which in this case is 12. 12 times half is 6. 18 minus 6 is 12. The same value that we obtained before, right? Right. So finally, the last Lagrange multiplier problem. We're dealing with the maximum value of x, y, z subject to these two planes, x plus y plus z to be 40 and x plus y minus z to be 0. So again, we provide some method here. There's 2 methods, not 3 methods. Apologies. So we consider the 2 constraint Lagrange multiplier setting, which is L xyz lambda mu equals to xyz target function minus lambda times the first constraint and mu times the second constraint. So again, we observe that since those are plane, so you have a constant normal vector, right? The gradient will be a constant. And those are not parallel, those are not zero, which means that your Lagrange multiplier method actually works. So by solving the equation, gradient being zero, you have this, and also the two constraints. So there's a bunch of ways to do this. In my case, I see these two guys first. You see that yz must equal to xz, right? And this tells you that x is equal to y or z equal to 0. So here you see that z can never be 0 because actually if z is 0, then x plus y is both 4D and 0, which is not possible. So the only possible situation for 11 and 12 tells you that x must be 1. Plugging that back into 14 and 15, you can get that the only possible solution would be 10, 10, 20. So that critical point plugging back into the function xyz gives you a maximum value of 2000, right? So the second method is, again, parameterization, because the intersection between two planes is simply a line, right? So you should be able to parameterize that line by a single parameter. In this case, a line can be solved by finding out the point that it passes through and also the directional vector, right? Since we're dealing with two planes, the directional vector is given by the cross product between the number vector of these two planes, which is 1, 1, 1, and 1, 1 minus 1. And you get -2 to 0. And you can find any particular point lying on that curve. In this case, I choose 10, 10, 20, plus the directional vector times a parameter t. So plugging that line into the function that we are interested in, you get this guy, which if you simplify, you get 4t times 25 minus t squared. So we see that this actually achieves a maximum value at t equals to 0, right? And that is 2000. And obviously, when t goes away from 0, either going to plus infinity or minus infinity, this guy always tends to minus infinity, which means that f of t has no absolute minimum. But whatever, when t is 0, which means that we're dealing with this point, you always have the maximum being 2000. Okay? Right. So that concludes for our discussion on different types of optimization problem. I try to cover like as much as possible. So I would say the difficulty will be similar. And you can obviously try out the exercise I provide in the back of the article. And yeah, I will see you guys in the integration part, which we will discuss double integral, triple integral, and also different transformation of variable to make life easier. See you guys.